tonight. So what we'll be looking at is rational functions. And rational functions, like if you're going to be somebody that takes calculus as a part of your major, well, you start like when I teach business calc or calc 1, first week of the semester, we're already talking about rational functions and how they deal with the idea of a limit. So first of all, let me just give you information on what we mean by a rational function. We've already looked at that before. So what it really means is you have a fraction, and the numerator and denominator are polynomials. So think of a rational function as a ratio of polynomials. If you have a polynomial on top and a polynomial on bottom, then you're going to have a rational function. And that denominator has to have at least a degree of 1. So here's some examples. Just write down and create some examples. So all I need to do is put a polynomial in top. Polynomials is what we've been talking about. Those are sums and differences of powers of x. That's a polynomial. It's a quadratic. The denominator, let's just put something like x to the third minus 1. So that would be a rational function, okay? A second example would be f of x equals 2. 2 is a polynomial because 2 is really 2x to the 0. 2 is a 0-degree polynomial, so it's okay to just have a number in the numerator. The denominator, we could have something like x plus 1. And again, you have to have at least, the denominator has to have a highest power of 1 at least. So those are two examples of polynomials. Here's something that is not a polynomial. Okay, if you had like x squared minus 2x over 2, that's not a polynomial because that denominator doesn't have a high enough power. That would be 2x to the 0. That denominator has to at least have a power of 1 on the x, anything bigger. So that's kind of what your rational functions are going to look like. The numerator can be a number, but the denominator cannot be a number. You have to have at least 1 power of x in the denominator always. All right, so that's what we're going to be looking at is rational functions, which we've already looked at before. And we've talked about domain before. And, I think on your first test, there were problems where I had you do a domain of a rational function. Already done it. So the idea is the domain is going to be all real numbers except where the denominator is 0. So when you've got a fraction, the one thing a denominator cannot be is 0. So your job when you figure out the domain of a rational function is try to figure out what makes the denominator 0. Often you can do that in your head. Sometimes you can't do it in your head. Okay? So what we're going to basically do on here is whenever you do a domain of a rational function, all you care about is the denominator only. You don't even need to pay any attention to the numerator. So what you're always going to do is set the denominator equal to 0, and then you're going to solve that, whatever that equation is. Okay, so all I'm going to do on this problem is just do x plus 5 equals 0. And I'm going to solve that equation, which you can do in your head. If you want to write the steps, you would subtract 5 from both sides, so you'd have x equals negative 5. So what that's going to mean is the domain is going to be everything except that. So just in words, it will be every number except negative 5, because negative 5 causes the denominator to be 0. So when you write your domain, we talked about set builder notation early in the semester. We usually do a set brace, then we say x, and then the such that bar. If I say write in set builder, that's just kind of the general way that you write that out. And then all you got to do is just say x is not equal to negative 5. And when you say that, you're telling me that it can be everything except negative 5. Okay, so you just write that like that, and that's good enough. Interval notation would be everything for negative 5, so you would write negative infinity to negative 5. You would put a parenthesis on negative 5, then you would start over again and go negative 5 to infinity like that. So the reason that you don't want to have a bracket on negative 5, because again, a bracket on negative 5, then you're telling me that it's okay for it to be negative 5. So those parentheses are saying that you can't be -5. Okay, we've talked about that before. That makes sense to everybody. Okay, so no brackets on that. So that would be how you do the first one, is like that. And the technique that I'm going to be doing on all these problems is exactly the same thing. So I go to the next problem, I take the denominator, I set that equal to 0. You can either factor that, or you can add 9 to both sides and do the square root property. It doesn't matter. That's up to you. Okay, so let's just do this. Let's just add 9 to both sides. We get x squared equals 9. And remember, like we learned way back at the beginning of the semester, every time you do a square root of both sides, don't forget that you're going to have a plus or minus answer. Square root of 9 is 3. So basically, our domain would be every number except -3 and 3. Okay, so that's what you're doing. You're just figuring out what makes the denominator 0. So in set builder notation, you would say set of x, and then you tell me what x can't be. Okay, and if you want to just write that as plus minus 3, that's okay. You can abbreviate that if you want to write that like that, that's fine. In interval notation, you have to kind of write 3 intervals. So you would say -infinity to -3, so it would be everything less than -3. It would be everything between -3 and 3, and then it would be everything bigger than 3. So you have to write out those 3 intervals when you're writing that domain. Okay, so again, keep it simple. If you're doing a domain of a rational function, you look at the denominator, you figure out what makes the denominator 0. And the domain will always be everything except what makes the denominator 0. Does that make sense to everybody, what I'm doing? Okay, right. Okay, I'll do one more example, and I'm going to have you do some problems here on some of this stuff. So what we do on this one is exactly the same thing. You don't pay any attention to the numerator when you're doing a domain. So just take x squared minus 2x minus 15 equals 0. Okay, how do you solve that equation? That's a quadratic equation, so what do you do? Got 2 choices, really. You got 3 choices, really. Factor, quadratic formula, complete the square. Which one is the best? Which one's the least amount of work? Factoring. Okay, if something factors, factor it. Okay, and you're going to find that this one factors. Your first term is just going to be x and x. Your last term is going to be 15. So what are 2 numbers that multiply to give 15 that add up to -2? 3 and 5. Right, 3 times 5 is 15. Okay, and then that inner term would be 3x. That outer term would be 5x. If you're going to make that add up to the middle term of -2x, then you're going to need to have a -5 and a +3. Okay, so that's how that factors. Okay, so factoring is always going to be there. And the better you get with factoring now, if you're going to take calculus or pre-calc, that saves you one big thing, because a lot of my calculus students need to still work extensively on their factoring skills. Okay, now you can solve these 2 equations in your head. I have no problem with you doing this in your head. That would give x equals -3. This one over here would give x equals 5. So remember, we're looking for the domain as everything except those 2, because those 2 things cause the denominator to be 0. So in set builder notation, you would say set of x. You would say x is not equal to -3. Then you could say comma x is not equal to 5. There's no shortcut on that. You just need to list that out. Okay. Now, when you do this in interval notation, you got 3 intervals. You have to be less than -3. So you would write that as -infinity to -3. You would have to be between -3 and 5. Make sure everything's in order. -3 comes before 5. And then finally, it would be everything bigger than 5. So that's how you would do that. So that's 3 examples of different things that can happen in the denominator. Okay, so that's how you figure out a domain as you run through that process. Okay, all right, so there's 4 problems at the bottom of the page. So I want everybody to try to work through these 4 problems. You can compare answers and just kind of see if you're on the right track. Everybody's kind of spread out in this class, so Be nice if you kind of get a little closer to somebody just to compare and contrast answers. Now I'll walk around, see if you need any help with that, and just kind of see how you're doing. But you want to just check and make sure that you've got everything good here. I didn't see anybody have any problem with number 1. So it's just basically x cannot be negative 5/3. So that's your set builder and interval. The next one, factoring, I think everybody was successful factoring that as x plus 2, x plus 8. So x can't be negative 2 and it can't be negative 8. So I just wrote set builder, set of x. It can't be negative 2, it can't be negative 8. Doesn't matter which order you put that in. Interval notation is pretty important on this one. Negative 8 and negative 2 go in that order. So you're going to be less than negative 8. So that's why you're going to have negative infinity to negative 8. You're going to be in the middle of negative 8 and negative 2. And that's going to be in the right order. Negative 8 comma negative 2. And then finally everything bigger than negative 2 like that. Okay, so sometimes some students write their interval notation better if they just draw a little picture of it. Okay, so the last one, I don't know if anybody factored on number 3. What I think most of you did on number 3, which is perfectly acceptable, is just added 2 to both sides and got 2x squared is equal to 2, then divided by 2 to get x squared equals 1, then did the square to both sides to get x equals plus minus 1. That's what it looked like everybody did, which is perfectly acceptable. What I did is I took a 2 out as a common factor, and then this is a difference of 2 squares, so I can factor x squared minus 1 as x plus 1, x minus 1. Either way you look at it, you're still going to get negative 1 and 1, so you can write set builder as x is not equal to plus minus 1, and then you can see how I did the interval notation is below negative 1, between negative 1 and 1, and then bigger than 1, like that, okay? So that's how that goes. And then on the last one, number 4, it's trial and error factoring. The first term is 2x squared, so you're going to have a 2x and an x. That's all you can have. Your last term is 5, so you can either have a 1 and 5 or a 5 and 1. And the way that I've been trying to kind of help people to learn how to factor the more complex ones is just try to do this little visual. So if you've got 2x and 1, then you got x and 5, okay, that's going to be a 1x. That's going to come together to make a 10x. You're trying to make that add up to negative 9x. So if you take the time to write that on your paper, then it's pretty easy to see that that goes like that, okay? So that means the 1 has to be positive and the 5 has to be negative. And then you can set each factor equal to 0 and solve. So ultimately, you can't be 5 and you can't be negative 1/2. Okay, yes?
Can you please do that one using the quadratic?
Sure. Yeah, I noticed you were going the quadratic formula, which is okay. So you probably made some sort of arithmetic mistake on this. So if you did the quadratic formula, you would have negative b, so it would be negative 9, plus or minus the square root of negative b squared minus 4ac all over 2a, like that. So you can see if you got what I got, that would be 9 plus or minus square root of 81 plus, and what would that be, 40 all over 4, like that. So now you would have 9 plus or minus square root of 121 over 4. Did you get to that point, or?
Yeah.
Okay, so here's what, that's what I thought. Because students always do that fine, because that's arithmetic. Square root of 121 is 11. Okay, now you got to do this. You got to do 9 plus 11 over 4 and work that out. And you got to do 9 minus 11 over 4. That gives 20 over 4, which is 5. This gives negative 2 over 4, which reduces to negative 1/2. I know I'm doing that fast, but I saw what you're doing on your paper. You got to this point here. Now it's just a matter of doing 9 plus 11 over 4, 9 minus 11 over 4.
And then how could you use, do you have to go backwards to put them into the factor?
Yeah, and actually you would probably never get this, but you can write it like, I mean, if you were going backwards, it would be like x plus 1/2 and then x minus 5. So you get the x minus 5 for sure. Okay, And then what happens kind of on this, if you take this part, x plus 1/2, and if you multiply that by 2, you get 2x plus 1. Okay? You want to try to get better at your factoring so that you don't have to do that, but it wouldn't be wrong to do that. Okay? If you have trouble with factoring, that's what you would want to do as a student. Okay? Okay, does anybody have questions about that then? Okay, so what we're going to look at next, what I wanted to mainly get through today is domain, but I want to look at asymptotes and what we mean by asymptotes of rational functions. Okay? All right, so let's go to the next page there. You got everything written down, Carla, that you need to get written down?
Yeah. Thank you.
Okay, you're good? Okay, all right. So what we're going to look next here is we're going to look at the vertical asymptotes on the next page and talk about what a vertical asymptote is and what it basically means. So what you're going to find on a rational function is there's going to be places where the denominator is undefined. So what a vertical asymptote is it's where the reduced form is undefined. Okay, it's a little different than the domain because sometimes you can cancel out a factor on that. And what happens on a graph of a rational function is typically you're going to see graphs kind of break, and there's going to be these little breaks in here. These dashed lines that I'm writing on this are called asymptotes. So I'm going to kind of give you a little bit of an idea of what happens at a vertical asymptote. So a vertical asymptote is going to be a place where that function's undefined, the reduced function's undefined. In this particular graph right here, there's a couple things I want you to fill out. The vertical asymptote is this line right here, and that looks like it's going through -3. So we would say the equation of that vertical asymptote is x equals -3. The equation of a vertical line is always x equals whatever it goes through. It's x equals something, okay? Now, if you're going to take calculus, this will get you a little bit ahead of what you do the first week in a calculus class, really, is this is saying as x, and this arrow says as x approaches, just means you're getting close to. That arrow means you're getting close to -3, and that minus sign right there means from the left-hand side. So this is what this means. This is just the language of the notation. You have this asymptote at x equals -3. So look what happens to the graph. I'm going to make this graph get closer and closer and closer to the asymptote. What is happening to the graph? What's it doing? Isn't it just getting bigger and bigger and bigger forever? Okay, so what we would say is as we get close to the asymptote from the left-hand side, x gets big, so big is positive infinity. So we would say that is positive infinity. Okay, so you got to get used to the notation on this. Okay, the next thing right here, again, the arrow just says, you can think of it as approaches, gets close to, okay, if we're getting close to -3 from the right, and that's what that plus sign means right there, that plus sign means from the right. So if you're on the right side of that asymptote, just get on the graph. Okay, if I get closer to that asymptote, where's the graph going? It's going down, right? So since it's going down, that means it's getting small. So that means that's going to -infinity. So what's going to happen if you have a vertical asymptote? The graph is never going to touch the vertical asymptote because it can't, because you're undefined. And anytime you have a vertical asymptote, the graph's either just going to go up to infinity or it's going to go down to -infinity. It's possible that they could both go to infinity on that. But every time you have an asymptote, that's what will happen. Okay, it won't touch the asymptote, it'll just go get real big or it'll get real small. That's what happens on a vertical asymptote. Okay, let's look at this next graph. So this one, our vertical asymptotes are -3. So we would say x equals -3 would be that equation. The other one is x equals +3. Okay, then you just want to see if you're getting solid with what I'm talking about with this notation. So this right here says x is getting close to the asymptote of -3 from the left. Okay, so what's the graph doing? If you're on the left-hand side of the asymptote, you're going up, so that will be positive infinity. Okay, that's what that's saying. Okay, the next one says as you're getting close to the asymptote of x equals -3 from the right, then the graph is going down, so that's negative infinity. Okay, it's either got to be one of the two, all right? Then these next two statements are saying as x gets close to 3 from the left, what's the graph doing? The graph's going up, so it goes to positive infinity. Okay, if you're going from the right-hand side, the graph's also going up, so that also goes to positive infinity. So you're going to see that on your web work, homework some. It's just filling out that language. That's just saying, as I get close to the vertical asymptote, what's happened to the graph? It's either going up or it's going down. That's the difference between the two. That's the idea, okay? All right, so what we'll begin to do now is let's look at how you take a function and figure out its vertical asymptote. So I'll do several examples of that. Is everybody okay with that infinity, negative infinity stuff? Okay, either the graph goes up or it goes down. Okay, can't be anything else on a vertical asymptote. Okay, so here's how you actually take a function and find the asymptote. And we'll do a little graphing on this because that'll help you understand what you do. So basically, there's nothing you can cancel on this, so it's kind of like finding the domain. You just take that denominator and set it equal to 0. You can solve that equation in your head, add 1 to both sides, you're going to get x equals 1. So the equation of that vertical asymptote is x equals 1, okay? Now, do this on your calculator because you want to get an understanding by using your calculator to kind of help you visually see what happens when you have a vertical asymptote. So go to y1 and put in the function, and you have to put it in like this. You go 1 divided by, and that x minus 1 must be in parentheses. If you're not in parentheses, you're not graphing it right. Okay, general rule of thumb. Numerator in parentheses, denominator in parentheses. If you always do that, you'll never go wrong. Now, if I just graph that in a standard window, see how you got that break? When x is 1, you're undefined. And what's happening is if you come from the left, you're going to negative infinity. You come from the right, you're going to positive infinity. So you're always going to have these rational functions with vertical asymptotes have that break in them. They're either going to go, both are going to go up, both are going to go down, or they might go in different directions. But visually, that's what's going to happen on the problem, okay? All right, next problem. What we're going to do on this is we're going to factor. You can't do anything with the numerator. That doesn't factor, but the denominator does factor. So we would have x and x to get x squared. For 12, we would need to use 2 and 6. And then we'd have a plus 6 and we'd have a minus 2. Okay, again, kind of look at the FOIL. You would have a negative 2x for your inner term, a positive 6x for your outer term, which would add up to that given inner term of 0.4. Okay, so in this case, you're going to end up having 2 vertical asymptotes. So you're just going to take these 2 individual factors. You can do this in your head, or you can just set each thing equal to 0 and solve each equation. So if you do that, you would add 2 to both sides. You would get x equals 2 would be one of your vertical asymptotes. And over here, you would subtract 6, so you get x equals negative 6. So in this particular problem, there are 2 vertical asymptotes, okay, like that. So it's kind of like doing a domain. There is going to be a slight twist that I'll do, I think, on the next example. But put this in your calculator so you can kind of see what's visually going on in the problem. Okay, so if we put in, this problem has to be put in like this. You'd have to put in 2x plus 3 would have to be put in a set of parentheses. Then you would divide by, and then that denominator also must be in a set of parentheses like this. Okay, either put it in your calculator or watch what I do, because mainly I want you to see visually what in the world you're doing anyway. Okay, if I graph this, look what happens. Okay, what is happening at 2? If x is 2, you got that break in the graph. Okay, if x is -6, the other vertical asymptote, you have that break in the graph. So your little dashed lines aren't going to come out, but they're there. Okay, so you can tell they're right. Okay, and if you were to go to your table of values by going second graph, you're going to see errors popping up. An error pops up at -6, error pops up at 2. That's because you're undefined there. Okay, that's why there's an error, because the calculator is trying to divide by 0. So that's the idea. Okay, now watch this next one carefully. This one's kind of has a slight twist to it. So what you want to do is you want to try to factor and see if you can reduce this thing. Okay, so x plus 5, the numerator, don't do anything with it. Okay, how do you factor x squared minus 25? X plus 5, x minus 5. That's a difference of 2 squares. Okay, so factor that difference of 2 squares. Okay, do you see anything? If I was to simplify this, does anything like divide out or cancel or anything? Yeah, okay, one of them cancels. So the one that cancels is going to give you what we call a whole. The one that's left over is going to give you a vertical asymptote. Okay, so you're not going to have 2 vertical asymptotes on this. The one that's left over is going to give you that vertical asymptote. So if you take x plus 5 equals 0 and solve that equation, which you can do in your head, you get your whole at x equals -5. That's not a vertical asymptote because it was removed, it canceled out. The vertical asymptote comes from the factor that's left over. So that would be x minus 5 is 0. Add 5 to both sides, you're going to end up getting x equals 5 like that. Okay, so if something cancels, that gives you a hole in the graph. Okay, please graph this on your calculator so you can see what I mean by this. All right, so now we're going to go back to the original problem. The original problem was x plus 5 in the numerator divided by x squared minus 25 in the denominator. Got to put that in. I'm going to type graph. Now, these things will look kind of weird on these things too. You see this break right here. Now, you're not seeing like it did the other one. That graph is going straight up. It's just your calculator isn't going to always look the way the graph really is. So you have your vertical asymptote at 5. But over here at -5, if I traced at -5, it's going to give you this little thing right there. It's saying y doesn't exist because it doesn't. You would actually just have a little hole in the graph. So the way this graph on this problem looks is like this. Okay, you got 5, you got -5. You're going to end up having a vertical asymptote like that, and then the graph is going to go up kind of like that. It's going to go down kind of like this. And then when you get over here, there's just going to be this hole in the graph because you're undefined. Just a little bubble there. That's not going to show up on the graphing calculator, but it's there. And the reason it's there is because you are undefined. See, if you go to your table of values on this problem, you're going to see 2 errors pop up. Okay, you're going to have an error at -5, and you're also going to have an error at 5. So there's 2 of them there. They both pop up. Okay, one's a whole, one's an asymptote. The one that cancels is the whole. The one that's left over is the asymptote. Okay? All right, so to wrap up, let's do these problems at the bottom of the page. There's 5 problems. I want to see if we can do each of these. Okay. All right. Mainly what you want to do is you want to try to factor. And if something cancels, then you're going to have a hole. If something doesn't cancel, then you won't have a hole. You'll have vertical asymptote. So on this problem 1, 2, and 3, 2 of these are going to have vertical asymptotes. One of them is going to have a vertical asymptote and a hole because of that cancellation. Okay, so let's work on that for about 5 minutes, and let's see if we can do these okay, and then that'll get us, approximately halfway through the section. Then we'll need to talk about horizontal asymptotes and graphs a little bit on Thursday. Okay, so what you should have, number 1, you just have x equals -3/2. Everybody got that. Number 2, you did have a cancellation of x plus 4. So you have a hole at -4 and a vertical asymptote at 4. Okay, I don't think I saw much go wrong with that. Number 3, the factoring's a little harder. So if you factor the denominator, you have 3x plus 1, x plus 2. So you'll have 2 vertical asymptotes. Nothing canceled, so x equals -1/3, x equals -2. And then the problems at the bottom here, this is just saying you have a vertical asymptote at x equals 2. You had to read that graph right because it's going by 2's. So from the right, you have infinity. From the left, you have -infinity. Okay, and then over here, it's just kind of infinity, -infinity, 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 like that. That number 5 had 2 asymptotes. One is at -1, the other one's at 2. Okay? So I think we did pretty well with that. Okay? Any questions about anything? Okay. Now, if you guys didn't watch those videos in 5.4 and 5.5, you want to do them now. Do them now. Get it done. Because I've got tests next week. All I could do today was do an overview of 5.4 and 5.5. The rest of them, work them out. Watch the video.